Hello, everyone. Today we are going to talk about Taylor and Maclaurin series. So we are kind of done with some simple representations of functions as series. Remember that the function 1 over 1 minus x can be represented as a sum of series like 1 plus x squared and so on, which is going to look like x to the power of n and from 0 to infinity, right? We also kind of did some derivatives of this, like we integrated this series, we differentiated this series, we squared x, but that's almost all we can get from this series. Like we have ln, we have tangent inverse, right? We do have the series for ln plus minus x. We also have tangent inverse of x series, but that's almost all we can have. Can we represent something else as a series? Something like e to the power of x, for example, or sine of x. You know that neither e to the power of x or sine of x are not looking like either like having derivative looking like this or integral looking like 1 over 1 minus x. So we need to invent something different. How are we going to do it? We are going to start with exponential function. And imagine that we do know the series for exponential function. We just don't know the coefficient. We know that like the series is going to look like general power series. C0, C1x, C2x squared, C3x cubed. And this is just general power series centered at 0. Right? Now, if we have a goal to find these coefficients, we don't know these coefficients because that's just general power series, right? How we can do it? Please watch how I do this because this is going to be a general method of finding coefficients for any differentiable function. I'm going to set up x equals 0 and calculate left and right side of my expression. So e to the power of 0 here. And over here, if I plug in zeros everywhere, I'm just going to get C0, right? I know that e to the power of 0 is equal to 1. So my conclusion is that C0 equals to 1 in this expression. What I'm going to do next, to get C1, I'm going to differentiate my left and right side of the series. You remember that in some cases we can do this, but actually, of course, we need to know that the series is convergent and the radius of convergence. But let's imagine that we can do this differentiation. So I'm going to differentiate it once. So this, I'm going to write down that that's a first derivative at 0. So I differentiate everything and plug in 0 again. So derivative of exponential function is e to the power of x, right? And I plug in 0. Derivative of my series is going to be, the first coefficient is going to disappear. We do know that it equals to 1, but with the differentiated, it's going to disappear. A second term is going to give me c1, and x is going to disappear because derivative of x is equal to 1, right? Next term is going to give me 2 c2x. Why does it happen? I differentiate x squared, it's 2x, right? Next term is going to give me 3 c3x squared. Again, I differentiate x cubed, it's 3x squared, right? And so on. And if I plug in 0 instead of x, all these terms are going to be equal to 0, just because when x equals 0, all of them are having x. So and e to the power of 0 is again equal to 1. So my c1 is also equal to 1. My conclusion over here is c1 equals to 1. I'm going to repeat this process several more times and then kind of give a general formula. So I'm going to calculate a second derivative. To calculate a second derivative at 0, I'm going to differentiate my first derivative. And exponential function, again, is going to give me e to the power of x, and it's still going to be equal to 1. And when I differentiate this expression, C1 is going to disappear because it's a constant. And instead of the term with x, I'm going to just have 2c2x is going to disappear because derivative of x is equal to 1, right? Next term is going to give me 3 by 2c3x, because when I differentiate x squared, I'm going to get 2x, right? Well, I don't have next term here, but if I kind of imagine what kind of next term I'm supposed to have, I'm supposed to have here c4x to the power of 4, right? It's going to give me 4c4x cubed. And when I differentiate it, it's going to give me 4 by 3 C4x squared, and so on. And again, when I plug in x equals 0, all these terms are going to be zeros because they all have x. X is equal to 0. So what I'm going to have? Well, for C2 expression is not like C2 equals 1, but C2 is equal 1 over 2, right? So my conclusion is C2 equals 1 over 2. And you see what I'm doing? I'm doing differentiation to remove the x. And one term is going to usually, the first one is going to lose x, and all other terms are going to have x to certain power. And all of them are going to disappear because when we set up x equals to 0, they disappear. And we will be able to calculate the constant. Now, guys, I'm not going to do really differentiation, but I'm going to think like what is going to happen on the next step. On the next step, I'm still going to have 1 on this side because exponential function is very convenient. Derivative is equal to the same number all the time and same function, right? Then this term is disappearing and this term is going to produce actually what? 3 by 2 C3, right? From where C3 is going to be equal 1 over 3 by 2. Yes, I'm going to write down 3 by 2 as 3 by 2 by 1. And you probably are going to recognize 3 factorial, the product of all numbers from 3 to 1, 3 factorial. And now I can write down here 2 factorial because 2 factorial is actually 2 by 1, right? And this one I can write down as 1 factorial. Why I'm doing this? Because I'm trying to get a general formula. How general formula is going to look? Imagine that I differentiate everything n times. What I'm going to get, guys? I'm going to still have 1 on this side, right? What is going to happen on this side? Well, when I differentiate it 3 times, I'm getting constant C3. So when I differentiate it n times, I'm going to get constant n, right? But before I clear constant n from x to the power of n, I'm going to write down in parentheses, the term is Cn x to the power of n. Before I remove this x to the power of n, I'll need to differentiate it n times because I differentiated first time and the power is 1 unit less, and then second time 1 more unit less, and so on. So what I'm going to get, the first time I differentiated as n, the second time I differentiated as n minus 1, the third time I differentiated n minus 2, and until I reach the last like times 3, 2. I'm not going to write down 1, but actually when we differentiate x to the power of 1, that's 1 over here and x to the power of 0. And then it's going to be Cn. So this expression is nothing else than n factorial, which I already have everywhere, right? And for Cn, I'm going to have a formula 1 over n factorial equals Cn. So guys, now I'm going to summarize all my calculations and write down actual exponential function as a series. E to the power of x, and my C0 is equal to 1. Where is it? C0 equals to 1. C1 equals 1 over 1 factorial plus 1 over 1 factorial x plus 1 over 2 factorial x squared plus 1 over 3 factorial this one x cubed plus lots of terms, and eventually we are going to have term 1 over n factorial x to the power of n, and actually there are going to be infinitely many of them, right? Because it's infinite series. Well, it's very easy to remember series, right? What we have? We have powers of x, and denominators are factorials. Actually, guys, you even can write down that this is divided over 0 factorial. If you remember, 0 factorial equals to 1. So in general, you can write it down as e to the power of x equals sigma x to the power of n over n factorial n from 0 to infinity. We got a series for exponential function. Very nice. I'm going to investigate a little bit this series, like how much it's convergent and everything else about this series, because, well, I'll need to know like how this series is going to behave. I'm going to use a ratio test. So I'm going to calculate limit as n approaches infinity of an plus 1 over an absolute value. It's going to be limit. Well, my n plus 1 is x to the power of n plus 1 over n plus 1 factorial and x to the power of n over n factorial. Actually, guys, we did it already one time when we were doing this radius convergency, and we did this series, and I told you that's exponential function, but now we know that it's exponential function. Let's simplify a little bit this limit. And from x's, we are just going to get x, right? And from factorials, n factorial over n plus 1 factorial. We remember that n plus 1 factorial is n plus 1 actually by n factorial, and we are going to cancel n factorial. So I don't want to stop the line over here. I'm going to move everything a little bit to the left. I'm going to have a limit as x divided over n, absolute value, n goes to infinity. Remember, guys, that was one of my examples when a series had infinite radius of convergency, because no matter what is x, when you divide it by infinity, it's going to give you 0. And 0 is always less than 1. So this series is convergent for any axis from a little bit noise. My cat is trying to get into the room. So as I said, that's going to mean that it's convergent for x from negative infinity to positive infinity, all number line, or radius of convergence is equal to infinity. And we remember that if we have a series with radius of convergence equals to infinity, you can differentiate it, you can integrate it, and the radius of convergence of that series is still going to be infinity, and that's going to be convergent. Okay, we're not going to prove that it's going to be convergent to e to the power of x. You can read it in the book, but like that's about like how we find actually the series for exponential function. And that's kind of easy to remember exponential function, right? Now, guys, I want to consider a little modification of this series before we move to more general formulas. Yeah, my cat finally got into the room. Was not happy that I did not open him the door. What if we consider a slightly modified exponential function? E to the power of 5x. You know how I like 5x. How do we represent it as a series? Well, again, write down C0, C1x, C2x squared, and start doing this x equals 0 first. And 0 is going to give me what? E to the power of 0, which is 1, and C0. So C0 equals 1. And then we do differentiation. I'm going to write down that it's derivative of x equals 0. And again, what are we going to have? Derivative over here is going to give me what? Derivative of exponential function is going to give me what? 5 e to the power of 5x. If I plug in 0 here, I'm just going to get 5. On this side, nothing is going to change. So I'm going to just like kill this term differentiating once, and this term is going to give me C1. So my C1 is going to be equal to 5. I'm going to do second derivative, and maybe I'm going to do the third derivative to make it more like visible. When I do second derivative, I'll differentiating this expression, and I'm going to get like 5 squared because I differentiate e to the power of 5x, and that's e to the power of 5x, and I differentiate 5x is going to give me extra 5, right? And extra 5, this is going to become 1 at 0, so extra 5 is going to be 5 squared. And what is going to happen to C2? Well, first, when I differentiated it first time, it's 2, differentiated second time is 1, and then C2. So actually, C2 equals 5 squared over 2 factorial. I'm going to do one more derivative, and then we're going to have a general rule x equals 0. It's going to be, well, we differentiated 3 times, I'm going to have 5 to the power of 3, right? And over here, it's going to be 3 by 2 by 1 C3. From where C3 is going to be equal 5 to the power of 3 factorial. Now, guys, I'm going to put everything back into a series, and let's see if we can make a kind of conclusion from how it looks. So C1 equals 1. C0 equals 1, C1 equals 5x, C2 equals 5 square x square over 2 factorial, 5 cube x cube over 3 factorial, it's C3, and so on. You see that x, the power of x, is similar to the power of 5. Why does it happen? Well, because you differentiated one time, and this factor is jumping in front, and that's going to produce like extra factor. So what you can do actually, guys, you can represent it as a normal power series like we have it for exponential function, but let me write it down. My pen stopped. Whenever I use a eraser, sometimes my pen just stops. Yeah, it writes also like 10,000 ones. That's 1. I'm going to write down 5x in parentheses. Then 5x squared over 2 factorial. 5x cubed over 3 factorial. If you compare it with general exponential function, e to the power of x, which is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, you're going to see that what we did actually, we just did substitution of 5x instead of like the power, instead of x's. So that's going to be how it works. If you have a linear factor, which you multiply by your x, you're just going to plug in your combination into the function, okay? Same is going to have with a square. Actually, the point here is that whatever function over here is sitting, it's going to have 0 at 0. If this happens, then you can just put function as of x. In most of the cases, it's not going to like look nice, but for example, if you have like linear factor by x, it's going to just multiply this linear factor by x into original series. Also, if you have a quadratic, cubic expression, it's going to work. Okay, now guys, I'm going to repeat this process one more time with a sine function, and then maybe give you a general formula of a series centered at 0. So, example number 2, sine of x. I'm going to write down c0 plus c1x plus c2x squared. Again, this series is not going to change because it's a standard power series, right? Centered at 0. I'm going to do x equals 0, and I'm going to have sine equals to 0 and c0 equals to 0. So that's it. c0 equals to 0. Sometimes happens. And the first derivative at x equals 0 is going to give me derivative of sine is cosine, right? Cosine of 0 is equal to 1. So, and here I'm going to have c1. c1 equals to 1. c1 equals to 1. Second derivative. Second derivative at 0 is derivative of cosine is what? Minus sine of x. And it's going to be equal to 0 because sine at 0 is 0. What are we going to have over here? 2 by 1 c2, right? Just differentiation. Well, the third derivative is 0 minus sine. If I differentiate minus sine, I'm going to get minus cosine of x. And that's going to be equal to minus 1, right? If I plug in 0 here. Remember, cosine of 0 is not equal to 0. It equals to 1. But because we do have minus in front, we're going to have 3 by 2 by 1 c3, from where c3 is going to be minus 1 over 3 factorial. So far, guys, we just have two numerical terms like two other terms. This one means C2 equals 0 just because it was 0. Well, guys, I'm going to do one more step to show you what is going to happen like with all of the terms. So I differentiate the cosine, negative cosine, I'm going to get sine of x. Why? Well, just because cosine derivative is negative sine and the extra minus is going to give me. That's going to be 4 by 3 by 2 by 1, C4, from where C4 equals to 0. Now, guys, you probably can predict what is going to be next. You see that all terms where we have sine are going to give us constant equals to 0. And constants are even numbers. So even constants are equal to 0. Even C0 is kind of even constant equals to 0. Odd numbers are going to be just kind of whatever we had for exponential function with factorials. The only difference is that sometimes we are going to have minus and sometimes plus. If you look carefully at what we have over here, you see that we started with sine. Actually, this 0 is what? That's a sine of 0, right? Is it sine, then move to cosine, negative cosine, and sine again. Now we are going to kind of copy then cosine minus cosine, and then repeat everything. So actually we did a full turn of different coefficients. Now we can just write the series for sine of x. Sine of x is going to be c0, c1 is equal to 1, so it's going to be x. There is no c2, so no quadratic term, minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the power of 5 minus 1 over 7 factorial x to the power of 7, and some other terms. All terms are going to be odd terms. Maybe it's understandable because sine is by itself odd function, right? And factorials are going to correspond to the powers. We are going to have alternation because like some derivatives are going to be negative, but it's going to be just like full alternation. Guys, I don't want to do cosine just because it's going to be basically very similar example. Usually in class, we just do it in class. So we will try to do cosine in class. I'm just going to give you the answer. So for cosine, the series is going to look like this. 1 minus x squared over 2 factorial plus x to the power of 4 over 4 factorial minus x to the power of 6 over 6 factorial and so on. So if you look at cosine series, you see that it's built mostly out of even functions like 1, x squared, x to the power of 4, to the power of 6. There is alternation, minus, plus, minus, plus, minus, plus, minus. Factorials are corresponding to the powers. So basically that's it. You see that just using general representation in this method of differentiation and setting x to 0 is giving us whole new 3 functions, right? So if I wish to write down a general formula for how the series is going to look, what is going to happen? Imagine that I'm going to represent function f of x, not specific e or sine or cosine. So how my term is going to be built? Let me go back to exponential function somewhere. I was doing it over here. Do you see that actually I'm taking the derivative and setting 0, and then I have n factorial cn on this side. So term number n, I'm going to write it down separately. Term number n is going to look like f nth derivative at 0 divided over n factorial. So if you write it down as in a sigma notation, you're going to have f nth derivative at 0 over n factorial multiplied by x to the power of n. N goes from 0 to infinity. And n equals 0. When derivative is 0, actually we mean the function itself. Derivative is 1, the first derivative, and derivative is 2, the second derivative, and so on. That's general formula for series centered at 0. Also known as Maclaurin series. Okay, so what if we want a series not centered at 0? And what I mean by that? Example number 3. Imagine that I have a function f of x, but I represent it as a series centered at a. That's a general representation of power series centered at a, right? I'm going to start doing the same operation I was doing for x equals 0. But to benefit from that operation, you cannot set up x equals 0 here. If I do it, I'm going to get like c1 multiplied by minus a. I need to turn it into 0. If I want to do this, I set x actually to a. And let's imagine that I calculate f of a. F of a, basically all this is going to be zeros, and I'm just going to have c0. F prime of a is going to be what? this term disappears. This one is going to lose the multiple, and that's going to be just C1. And this one is going to still have 1x minus a. And if I set up x equals a, it's going to be 0. And the second derivative at a is going to be what? Because I differentiated 2 times, it's 2 by 1 C2, right? And all other terms are going to become zeros by the same reason, because I'm setting x equals to a, which means that I'm setting co-parentheses to 0. And basically, the function is kind of going to give me very similar formula. Cn is going to be what? Derivative n at point a divided over n factorial. And general formula for representation of a function at any point, not necessarily at 0, is going to look like n factorial, and here x minus a. So this series is centered at a. Whatever number is here, that's going to be a center of the series. These series are called Taylor series. And of course, you can set in Taylor series a equals to 0, and they are going to become like centered at 0 Taylor series. But mathematicians separately name them Maclaurin series. Okay, well, we can probably calculate something not at 0. Maybe I'll do cosine series, because I did not do general Maclaurin series cosine. I'm going to do cosine at a different point. So example number 3, no, number 4, I think. Number 3 we already have. I'm going to consider cosine of x, and I'm going to represent it as Taylor series centered at a equals pi over 4. That. Just to see how everything is going to look. So, well, guys, we actually can try to use general formula, but because cosine is going to give you all these different derivatives at pi over 4, maybe it makes sense to calculate first few terms. So what we do, cosine of pi over 4 equals to what? 1 over square root of 2, right? So my first term, or C0, which is just a function, this one, is going to be 1 over square root of 2. Then my second one is a derivative of cosine, right? So derivative of cosine is what? Negative sine. If I plug in pi over 4, I'm going to get minus 1 over square root of 2. So C1 equals minus 1 over square root of 2. Differentiate one more time. Derivative of sine is cosine, right? Pi over 4. Remember that over here is going to be like 2 by 1 C2. So C2 equals, and minus cosine is negative 1 over square root of 2. Square pi over 4 is a very convenient number for sine and cosine, because it has basically the same numerical value for both sine and cosine, right? So I have minus 1 over square root of 2, 1 over 2 factorial. And I'm going to do one more. Differentiation of cosine is going to give me sine, again, without minus. And that pi over 4 is going to be just 1 over square root of 2. And it's going to be 3 by 2 by 1, C3, right? So from where C3 is going to be 1 over square root of 2, 3 factorial. Now, guys, I'm not going to calculate more of them. I'm just going to write them down, the ones which I calculated already. So I have 1 over square root of 2 plus, I'm supposed to use minus because it's a negative. Negative 1 over square root of 2, x minus pi over 4. My series is not centered at 0. Next one, minus 1 over square root of 2, 1 over 2 factorial, x minus pi over 4 squared. You guys can put factorial underneath of the parentheses. Maybe it's going to be more like looking a little bit better. And I think the book is doing this. But anyway, I'm going to do the last one. The last one is going to be positive, 1 over square root of 2. and x minus pi over 4 cubed over 3 factorial. So we are going to have alternating square root of 2, 1 over square root of 2. And this is a whole pattern, right? The next term is going to be like, we have positive, like positive, negative, negative, positive, and then it's going to be derivative of sine is going to be cosine again, and it's going to be positive, then two negatives, and then two positives. It's not like actually direct alternation, like, right? Usually, guys, when somebody is asking you to represent function somewhere not at zero, you're not expected to have a general formula because, well, in this case, general formula is still possible, but usually it's going to be kind of hard to write down general formula. So I would suggest you just calculate first few terms and kind of show the pattern how to create the next term. Okay? And typically that's going to be the problem. Calculate first few terms of Taylor series centered at that point. Now, guys, maybe we talk a little bit of how do we use Taylor series, how people are using Taylor series. And kind of there are many uses of Taylor series, but we're going to kind of start with yeah, people are calling the all series centered at zero and non-centered at zero as Taylor series. And if they want to specifically point to centered at zero series, they're going to say Maclaurin series. Well, I think of the first one of the first uses is going to say goodbye to L'Hopital's rule. Imagine that we have a series limit like this. What we would do before we learned about Taylor series, we would just differentiate it. And you probably see that you will need to differentiate it twice. So use L'Hopital's rule 2 times. I'm going to represent each of these functions because I do know Taylor series at zero, Maclaurin series. I'm going to represent them as a series. You probably will tell me, oh, series are going to have infinitely many terms. Yes, guys, but watch how everything is going to work. 1 minus for cosine, it's 1 minus x squared over 2 factorial plus x to the power of 4 over 4 factorial and some other terms. Denominator, 1 plus x, exponential function. 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so on. How do I know all this series? Guys, you will need to memorize 3 basic Taylor series or 3 basic Maclaurin series, which are e to the power of x, sine of x, and cosine of x. The book also has tangent and has some inverses, but if you don't memorize them, no one is going to complain. You will need to know 3 basic exponential, sine, and cosine, like memorize them. So I'm going to start developing everything in this, like simplifying everything in this fraction. So you probably see that I can cancel 1 and 1, but the rest is not going to be canceled. That's going to be x squared over 2 factorial minus and minus, and minus x to the power of 4 over 4 factorial, and some other terms, minuses or pluses. Here, x, 1 cancels, x cancels. And I have minus x squared over 2 factorial minus, sorry, x cubed over 3 factorial, and so on. X goes to 0. Now, guys, what I'm going to do, I'm going to divide by x squared, numerator and denominator. I'm going to have 1 over 2 factorial minus x squared over 4 factorial and some other terms. And minus 1 over 2 factorial minus x over 3 factorial and some other terms. Now, guys, if I set up x equals to 0 in this expression, all terms over here are going to have x's, and they are going to be equal to 0 because when x equals to 0, it's going to turn everything to 0 here too. So we worry only about terms without zeros, and they're exactly the same terms, one with plus, one with minus. So final limit is equal to -1. And you don't need L'Hopital's rule. Actually, guys, using L'Hopital's rule, you are doing Taylor series because remember what you do. You differentiate it, right? What is this? What is this 1 over 2 factorial? It's a derivative, actually, right? How do we get it? It's a second derivative at 0. Same over here. So, because x squared, actually, the term of x squared is defined as second derivative. So basically you are doing that. Remember, I did not prove anything about L'Hopital's rule when we were doing it in chapter 6. And I said, later you are going to see why the rule is working. That's why the rule is working actually. Okay. I think maybe we should consider one more example. Okay. So a little bit more complicated. And again, I'm not going to use L'Hopital's rule anymore. I'm going to use a series. And I know the series for sine, and it's like what? The series for sine is x minus x cubed, odd numbers, right? But instead of x, I'm supposed to use 5x. So it's 5x, right, minus 5x cubed over 3 factorial. Yeah, guys, it's going to be very super boring to check every time the series if you need to use it. You will need to know them hard. 1 plus 3x. And for exponential function, the series is going to have 3x instead of x. So it's 1 plus 3x plus 3x squared over 2 factorial and so on, right? Standard exponential function, just substitution of 5x and 3x instead of argument. Now I'm going to start canceling everything. Cancel this, right? Cancel this, cancel this. And I'm going to have what? Limit. Here I'm going to have minus minus plus 5x cubed over 3 factorial, denominator 3x squared over 2 factorial. X goes to 0. Forgot x goes to 0 here. So guys, I'm going to move to next line. Guys, what I see over here, that of course there are other terms, right? There are other terms. I'm going to divide by x squared. I'm going to divide by the smallest of like numerator and denominator. Why? You're going to see, because if you divide by x cubed, you are going to get x in denominator, which is going to produce probably infinity as a term, right? So I'm going to divide by x squared, both numerator and denominator. And here, well, 5 cubed is 125. And if I divide by x squared, I'm going to have just x divided over 3 factorial plus some other terms with also x. And here I'm going to have 9. And here I'm going to have 3 factorial, and all other terms are going to have x because they're going to be x cubed. And if you divide by x cubed, it's going to produce, divide by x squared, it's going to produce 1x at least. So x goes to 0. Now, guys, when x goes to 0, this will go to 0, right? This is just a number. This will go to 0. This will go to 0. And what I'm going to have? I'm going to have 0 plus 0 divided over number, which is going to produce 0. And sometimes people think that 0 is not a kind of valid limit. So limit cannot be equal to 0. Yeah, limit can be equal to 0 also. Limit can be equal to infinity. Like with L'Hopital's rule, limits are not always numbers. Sometimes they are zeros, sometimes infinities. And here we do have limit going to 0 just because like you can check it. Using L'Hopital's rule, you are going to get the same answer. I will differentiate it twice and get exactly the same answer. Okay, so that was one of the applications. My next application is going to use the series to integrate. Remember, we were integrating something like the integral, which was non-elementary function. Use number 2. Integrate functions Why? Well, remember in chapter 7, I was telling you that there are some integrals which you cannot integrate and get the formula, non-elementary functions. This is one of them. So you cannot really find the formula because there is no way to differentiate something and get this expression, fortunately. So instead of finding, I'm going to find this integral, I don't know, from 0 to 1, for example, e to the power of negative x squared dx. I'm going to represent it as a series. Well, exponential series is well known, right? I'm going to just use it. Just my argument is going to be minus x squared, because when x equals 0, it equals to 0. So minus square and plus, I'm going to have minus x squared over 2 factorial. And guys, I'm going to put plus, but then minus x squared cubed over 3 factorial and so on, dx. Why we like to do this? Because power functions are very easy to integrate. Integral of 1 is x, right? Integral of x squared is x cubed over 3. Integral of x to the power of 4 is x to the power of 5 over 5. 2 factorial is going to stay. Here we are going to have x to the power of 6, x to the power of 7 over 7, 3 factorial, and so, right? And we are going to have some alternation because like sometimes we are going to have it squared, sometimes not squared. Okay. Maybe I'll do one more term. What do you think? What is going to be the next term? If like, can we guess? Well, we have odd powers, right? So it's x to the power of 9 probably over 9 or 4 factorial. And the next term is x to the power of 11 over 11, 5 factorial. Okay, that's enough. So we actually found the integral. We integrated as a series, and people are going to use series where they cannot find the actual function. Not only in integrals, also solving differential equations, for example. I'm going to plug in my numbers. Well, if I plug in 1, I'm going to have what? 1 minus 1 over 3 plus 1 over 5, 2 factorial, minus 1 over 7, 3 factorial, plus 1 over 9, 4 factorial, minus over 11, 5 factorial, and so on, right? If I plug in 0, that's going to be minus 0, which is going to give me no change. Yeah. So guys, we have a series. Remember that any partial sum estimates the sum of series. Basically, we need to know how many terms we'll need to use. Well, I don't know. I think that maybe we can keep like this 1, 2, 3, 4, 5 terms and see what is going to be remainder. Remember that for alternating series, remainder of n terms is less or equal than term bn plus 1, the next term, right? I'm going to calculate what is this term. It's easy to calculate because I know that 5 factorial is actually 120. So it's going to be 1 or 11, 20, and it's going to be 1 over 1, 3, 2, 0. Well, obviously it's more than 1000, so it's going to be less than 0, 0, 1. I don't have a calculator right now under my hand, so it's just my estimation. So what I see, if I drop this term, which is 1, 2, 3, 4, 5, number 6, term number 6, the remainder whole terms after that are going to be less than 0.01. So if I add up these terms, my accuracy is going to be pretty high, right? Just one digit. Like first digit is going to be correct after decimal point, the second digit correct, and the last digit is going to be like, well, plus minus 0.001. Well, that's another application. And I want to talk about the last application, which is going to use series for estimation of the function to estimate values of sine of x, cosine of x, and e to the power of x. Well, guys, you probably don't know that, but before we kind of got calculators, to find the cosine of, for example, 29 degrees, we were using Brady's tables. That's what I was using in school, actually. I didn't have calculator when I was in school. I think I got my first calculator when I was 15 on my 15th birthday. It was a scientific calculator, but that was my first calculator. Before, if I wanted to find sine of something which is not like 30 degrees or 45 degrees or 60 degrees, I had to open a little tiny book, which is called Brady's tables, and where I have all the values of sines of different degrees listed. Well, how these values were obtained? Well, let's look how the sine of x is going to behave. I'm going to show you one example. Remember that sine of x is a series x minus x cubed over 3 factorial plus x to the power of 5 over 5 factorial. It's supposed to be minus actually, and like similar way, right? If I want to estimate sine, I don't know, let's say 0.1. This value is actually not degrees, it's radians. I'm going to plug in 0.1 here minus 0.1 cube over 3 factorial plus 0.1 to the power of 5 over 5 factorial and so on. You see that we have alternating series, right? Alternating series. So remainder of alternating series is less than the first term we drop. For example, we decide to drop this term. How big is this term? 0.1 to the power of 5 over 120 because 5 factorial is 120. Well, 0.1, 2, 3, 4, that much. 0.1 to the power of 1, 1, 2, 3, 4, 5 over 120. This is more than 100. So actually term is going to be 0, 1, 2, 3, 4, 1. I think that's going to be the value. Maybe not. Maybe I placed too many zeros. Supposed to be 1, 2, 3, 1, 2, 3. No, that's correct. So actually, if I drop these terms, sum of only these two terms is going to give me the value of this sine with this accuracy. This is 10 to the negative 7. Wow. Your calculator is not going to give you better accuracy. And it's very easy to add these terms, right? That's what? 0.1 minus, well, this is what? 0.001 and 3 factorial, it's 3 by 2 by 1, which is basically 6. So it's 0.1 minus 0.001 divided over 6, which is going to give me minus, we do division, 0.0001 or the divided by 6, about 6, something like that. I'm trying to figure out what is going to be like the value, and I need to open my cell phone to use my calculator actually. So give me a second. Where is my calculator? Yes. So I have 1 minus 0.123. I think it's 16, but I'm not sure. I'm getting something like 0.99984. I think maybe that's not 16. Okay, I'm going to check now using my calculator what is precise value of sine of 0.1. So I'm going to put sine and then 0.1 close parenthesis. When I was subtracting, I subtracted it from 1, not from 0.1. That's why I got this big number. Let me fix it, guys. Sorry. Oh, give me a second. Okay, so guys, sorry, it took me a while to do calculations, but let's say I kind of did one, I missed a zero over here, and when I was calculating the value over here, which is 16, actually was 16 and more 6 after. So when you subtract 0.1 minus this 0.001666, you are going to get something like this. And if you take you take your calculator, calculate actual sine of 0.1. Just don't forget that 0.1 is in radians. You are going to have value 0.99833, and there is like 4 and some other digits. And if you start comparing, so 0 is correct, 9 is the same, another 9 is the same. So 3 digits are exactly 4 digits, 5 digits, 6 digits are going to be exactly same as the calculator gives us. Why? Because actually calculator is using this formula. Calculator does not have a big table of all values of sines and cosines recorded there. It's calculating them. Maybe not this specific formula, but something similar to this. So the only difference is going to happen over here, position number 7, I think. And that's where it's supposed to be, because you see, we dropped the remainder, which was term number 3 actually, and we kind of make uncertain position number 7, and that's going to be uncertainty, which is going to happen because this one is going to have 3 over here in position number 7, and actual is going to have 4, I think. Let me check it one more time. Sine 0.1. Oh no, too many zeros. 0.1. Yes, the next digit is 4 and then 6. So actually this digit is going to be 1 unit greater than one which two terms are giving us. Why we can do this? Well, guys, because actually for small values, these terms of alternating series are decreasing very, very rapidly because they are power series, right? And that's rapidly decreasing geometric series. Okay, I think that's all. So what you will need to remember first, how to find the Taylor series for not centered at 0 and centered at 0, how to use it to estimate the values of sine, cosine, and e to the power of x, how to use it to calculate without L'Hopital's rule, and how to use it to estimate integrals. Okay, I think that's all for today. I'm sorry for a long pause because I was trying to use my calculator and it was rotating all the time. Okay, so thank you very much and see you next lecture.